Howdy there, BMETs, and welcome back. I'd like to take a quick second and congratulate you on completing the first section of Course 102, and welcome you back to the Attention to Detail section, as I like to call it. In the first section, you learned about turning AC into DC with power supplies, but today we threw a 180-degree phase shift at you. Well, more like two. Today you learned about oscillators and how they turn DC into AC, so let's briefly discuss a generic oscillator and what that consists of. The purpose of an oscillator is to turn DC into sinusoidal AC. An oscillator consists of two circuits, the feedback circuit, which is responsible for developing the AC and determining the frequency. Real quick though, notice the amplitude loss from the input to the output of the feedback circuit. This brings me to my next circuit, the amplifier circuit, which is going to keep the signal boosted or amplified to keep the signal from tapering off. This is a process known as regenerative feedback. Lastly, I just want to talk about the phase shift. The amplifier, from the input to the output of the amplifier, there's a 180-degree phase shift, and from the input to the output of the feedback, there's another 180-degree phase shift, because we are creating AC for a full 360-degree sine wave. Now, let's talk about our first oscillator, the Hartley Oscillator. So the purpose of a Hartley oscillator is the same as our purpose of a regular oscillator, to turn DC into sinusoidal AC. The feedback circuit consists of two inductors and a capacitor, and the component values will be used to calculate frequency. The amplifier circuit consists of Q1 and all the associated components. It's basically your common emitter amplifier circuit you learned on days 1 and 2, but we just tied a feedback circuit to the input and output. As soon as VCC is applied, the feedback circuit produces oscillations and are amplified by our amplifier circuit. Now, watch regenerative feedback in action. The output gets fed back in as an input to the feedback circuit, and the output is 180 degrees out of phase from the input of the feedback. Also, notice that some amplitude was lost on the output, which is why it gets fed back into the amplifier circuit, which amplifies the AC and inverts it for another 180-degree phase shift. Lastly, frequency can be calculated by using the formula on the right. P.S. Don't forget to take the square root of LC. If you do, you're gonna have a bad day. Oh, and pro tip, the Hartley oscillator can be easily identified by the two inductors, which look similar to the handlebars of a Harley motorcycle. Next is the Colpitts Oscillator. The purpose is to turn DC into sinusoidal AC. The operation of the Colpitts is exactly the same as the Hartley. The key difference is the components of the feedback circuit. Notice that the Colpitts has two capacitors connected in series and one inductor. The amplifier circuit, as seen, is identical to the one before, our transistor and all the components. As soon as we apply VCC, the feedback circuit produces oscillations, and the amplifier's output just gets fed back in as an input to the feedback circuit through regenerative feedback. Just like before, we lost amplitude from the input to output of our feedback circuit and a 180-degree phase shift. Then it gets fed back into the amplifier circuit, which amplifies and inverts the AC for another 180-degree phase shift. You'll need to be able to calculate the frequency for the Colpitts as well, and the formula is the same. But remember, when calculating for capacitance, you have to calculate the caps in series like you would with resistors in parallel. So you have to use that reciprocal method. If you forget this, you're gonna have a bad time. But with that being said, let's move on to my favorite oscillator, the RC phase shift oscillator. Just like before, the purpose of an RC phase shift oscillator is to turn DC into sinusoidal AC, and it still has a feedback and amplifier circuit. The main difference is that the feedback circuit is made up of C1 through 3 and R1 through 3, as compared to a capacitor and an inductor earlier. The amplifier circuit is the same as before, it's just a common emitter amplifier circuit. As soon as VCC is applied, the developed AC is fed back into the feedback circuit at C1, and that AC, a fraction of a second after being felt on the left side of C1, starts it to charge and discharge through R1. Then a fraction of a second after that, the AC developed on the top of R1 causes C2 to charge and discharge through R2. Then, Another fraction of a second later, that AC developed on the top of R2 causes C3 to charge and discharge through R3, and the AC developed here is the input to the amplifier circuit. Now, each of those fractions of a second represent a 60-degree phase shift from the previous AC signal, or as I like to say, every time you pass a cap, you shift 60 degrees for a grand total of 180 degrees from the input to the output of the feedback circuit. So just like all of our oscillators, there's a 180 degree phase shift in the feedback circuit, and our common emitter gives us another 180 degree shift for a total of 360 degrees of our sine wave. Frequency can be calculated using the formula on the bottom right. Pro tip: since R1 and through R3 and C1 through C3 are equal value components, you can totally simplify the part in parentheses to just R1 times C1 times 3, just to save time and the risk of messing up. Now let's move on to our last oscillator, the Sawtooth Oscillator. In this circuit, we're going to take a square wave input and turn it into a sawtooth output, so it's kind of a change up from what we've been talking about. In this circuit, Q1 is a transistor switch, so that means it's operating between maximum current flow and no current flow, or you know this as saturation and cutoff. When the NPN transistor Q1 is off, on the low portion of the square wave, C2 will be charging because VCC will be felt on the collector, which will attract electrons to the plate of C2. Here, let's see that one more time. When Q1 turns on the high portion of the square wave, a low will be felt on the collector, and C2 will discharge. Let's see an instant replay on that. Now, notice how one square wave input creates one sawtooth output? That tells me that the frequency of the output is determined by the input. Hashtag no math required. Frequency in is equal to frequency out. So if you're doing math, you're probably wrong. Alright, thank you guys so much for listening today. Be sure to like and subscribe for updates on future videos. If you have any questions, feel free to post them in the comments below. And again, I just want to congratulate you guys on completing the first section of the course. Oh, and remember, when doing your calculations, be sure to measure twice and cut once. Oh, and as always, keep being awesome. BMET out.